Hey everyone, He-Hu here from LeetCode. Today we're solving LeetCode 1004. Max consecutive ones 3. This is a medium difficulty problem, and it comes under arrays and sliding window in the LeetCode 75 study plan. At first glance, this problem looks like we're simply counting consecutive ones. But there's an interesting twist. We're allowed to flip some zeros into ones. The question is, which zeros should we flip? And how do we find the longest possible sequence without trying every possibility? That's where today's interview pattern comes in. So, let's first understand exactly what the problem is asking. We're given a binary array called nums. That means every element is either 0 or 1. We're also given an integer k. The value of k tells us the maximum number of zeros we're allowed to flip into ones. Our goal is to find the longest contiguous subarray that can contain only ones after performing at most k flips. Notice two important things. First, the subarray must be contiguous. We cannot skip elements. Second, we're allowed to flip at most k zeros, not exactly k. That means using fewer flips is perfectly fine. Now let's understand this with an example. Suppose the array is 11100011110 and k is 2. Since we're allowed to flip at most 2 zeros, we need to choose them carefully. Let's say we flip the 2 zeros in the middle. Now the array looks like 1111110. Notice what happened. Those two flips connected two groups of ones into one much longer sequence. The longest consecutive ones now becomes 6. That's our answer. Now here's an important question. Do we have to flip the first 2 zeros we see? No. Different choices can produce different lengths. Our goal isn't just to flip zeros. It's to find the best possible window that uses at most k flips. Keep that idea in mind. It'll become very important later. But before we get there, let's think about the most straightforward solution. The simplest idea is easy. Let's consider every possible subarray. For each subarray, we count how many zeros it contains. If the number of zeros is less than or equal to k, then this subarray is valid. We calculate its length and compare it with our current answer. If the subarray contains more than k zeros, then it's invalid, so we ignore it. After checking every possible subarray, the longest valid one must be our answer. This solution is simple. It's easy to understand. So let's see how we'd write it. Let's convert that idea into code. First, we create a variable called maximum length. Initially, it's 0. Now we generate every possible subarray. The outer loop chooses the starting index. The inner loop extends the subarray one element at a time. As we extend the window, we keep track of how many zeros we've seen so far. Whenever we encounter a zero, we simply increment our zero count. Now we check one condition. Is the zero count less than or equal to k? If yes, this is a valid subarray. So we calculate its length and update maximum length if needed. If the zero count becomes greater than k, this subarray is no longer valid. We stop extending it and move to the next starting position. After checking every possible subarray, we simply return maximum length. The algorithm is easy to understand. But let's verify it with a dry run. Let's use a smaller example. The array is 10110 and k is 1. We start from the first element. The first subarray is 1. It contains 0 zeros. So it's valid. Its length is 1. Now extend the subarray. It becomes 1 0. The zero count is now 1. That's still within our limit. So this window is valid. Its length becomes 2. Extend again. Now the subarray is 101. The zero count is still 1. So the window is still valid. The length becomes 3. Extend again. Now we have 1011. Again only 1 0. So this window is valid. The length becomes 4. Now extend one more time. The subarray becomes 10110. Now the zero count becomes 2. But we're only allowed one flip. So this window is no longer valid. We stop here. Now we repeat the same process starting from the second element. Then the third. Then the fourth. Eventually, we've checked every possible subarray. The solution works correctly. But notice something. When we move to the next starting position, we repeat almost the same work all over again. That feels expensive. Maybe we can avoid starting from scratch every single time. Let's analyze the complexity. Suppose the array contains n elements. For every starting position, we may extend the subarray through almost the entire remaining array. That gives us roughly n squared operations. So the time complexity becomes O of n squared. Now let's talk about space. Apart from a few variables like the zero count and the maximum length, we don't create any extra data structure. So the space complexity is O of 1. The space usage is already optimal. But the running time isn't. We're restarting our search again and again. Can we somehow keep the useful part of the previous window, instead of rebuilding a new one every time? Let's think about what actually makes a window valid. Is it the number of ones? No. The only thing that matters is the number of zeros. As long as the window contains at most k zeros, we're allowed to flip them. That means the entire window can become all ones. So the window is valid. Now another question appears. What happens when we add one more element? If it's a 1, nothing changes. The window is still valid. If it's a 0, our zero count increases. The window may still be valid. But eventually, we'll reach a point where the number of zeros becomes greater than k. Now the window is invalid. Here's the important question. Should we throw away the entire window and start again? No. Most of the window is still useful. The only problem is that it contains one extra zero. So instead of restarting, we simply move the left side of the window. As the left pointer moves, elements leave the window. If a 1 leaves, nothing changes. If a 0 leaves, our zero count decreases. The moment the zero count becomes less than or equal to k, the window becomes valid again. That's the key observation. We never restart. We only do two things. Expand while the window is valid. Shrink only when it becomes invalid. This is called a variable size sliding window. Unlike the previous problems, the window size isn't fixed. It keeps growing and shrinking depending on whether the current window is valid. Now, let's see how we implement this idea. We'll use two pointers. Left and right. The right pointer keeps expanding the window. Whenever it encounters a 0, we increase our zero count. As long as the zero count is within k, the window is valid. So we simply calculate its length and update our answer. But the moment the zero count becomes greater than k, the window becomes invalid. Now we stop expanding. Instead, we move the left pointer until the window becomes valid again. Then we continue expanding with the right pointer. This process continues until we've processed the entire array. Now let's translate this idea into code. Now let's convert this idea into code. First, we initialize left to 0. We also create a variable called zero count. Initially, it's 0. And we create maximum length, which also starts at 0. Now we move the right pointer through the array. Whenever the right pointer sees a 0, we increment zero count. Now we check whether the current window is still valid. If zero count becomes greater than k, we start shrinking the window. As the left pointer moves, elements leave the window. If the outgoing element is a 0, we decrease zero count. We keep moving the left pointer until the window becomes valid again. Once the window is valid, we calculate its current length. That's simply right minus left plus 1. If this length is larger than maximum length, we update our answer. Then we continue moving the right pointer. After processing the entire array, we return maximum length. Notice something interesting. Every element enters the window only once. And every element leaves the window only once. That's why this solution is so efficient. Let's use the same example. The array is 1 0 1 1 0 and k is 1. Initially, both pointers start at the beginning. The first element is 1. The 0 count is still 0. The window is valid. Its length is 1. So maximum length becomes 1. Now move the right pointer. It reaches 0. The 0 count becomes 1. That's still within our limit. So the window is valid. Its length becomes 2. Update the answer. Move right again. Now we see 1. The 0 count doesn't change. The window is still valid. Its length becomes 3. Update the answer. Move right again. Another 1. Still no new 0. The window remains valid. Its length becomes 4. Update the answer. Now move right one last time. We reach 0. The 0 count becomes 2. Now the window is invalid. Because we're only allowed 1 0. So we begin moving the left pointer. The first element leaving the window is 1. The 0 count doesn't change. The window is still invalid. Move left again. Now a 0 leaves the window. The 0 count drops back to 1. Now the window is valid again. Its current length is 3. That's smaller than our best answer, so nothing changes. The right pointer has reached the end of the array. We're done. The longest valid window has length 4. Let's analyze the complexity. The right pointer visits every element exactly once. The left pointer also moves forward only once. Neither pointer ever moves backward. That means every element is processed at most twice. So the total time complexity is O of n. Now let's talk about space. We only use a few variables, the 2 pointers, the 0 count, and the maximum length. No extra arrays, no additional data structures. So the space complexity is O of 1. Let's quickly recap. We started with the brute force solution, for every starting position. We built a new subarray from scratch. The solution worked. But it repeated a lot of unnecessary work. Then we asked one important question. What actually makes a window valid? The answer was simple. The number of zeros. As long as 0 count is less than or equal to k, the window is valid. So we keep expanding it. The moment 0 count becomes greater than k, we don't restart. We simply shrink the window until it becomes valid again. That's the interview pattern to remember. For a fixed size window, the size never changes. But for a variable size window, the size depends on whether the current window is valid. Expand while the window is valid. Shrink when it becomes invalid. You'll see this pattern again and again in many sliding window problems. And that's how we solve LeetCode 1004. Max consecutive ones 3. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode. Thanks for watching. This is Hihu, signing off. Keep practicing. And I'll see you in the next one.